Welcome back everyone. In this lecture I will introduce what is an order of an element inside the groups. Okay. So then later once we get familiar with this order, then I will introduce what is called cyclic groups, and then I will give various characterization of cyclic groups. Okay, let's begin. So let us start with finite group, and then we proved one results. Let's recall that about finite group. If G is a finite group and A is an element in G, so then we proved that there exist R in N such that A power R is identity. So this is something we already proved. So this is a fact. So the way we proved it, so you look at this set A square, A cube and so on. So this is supposed to be a subset of G. So since this looks like having infinitely many elements, but being a subset of G, this has to be finite. So the fact that this set is finite actually gives us R such that A power R is identity. Okay. So this is something we already seen. So now this actually somewhat motivates us to actually look for smallest R such that A power R is identity. So that is the definition of order of an element. Okay. So now start with the general group G. So let us start with G being just a general group, okay, not necessarily finite, just a group, and take one element X in G. Okay. Assume that there exists R such that X power R is identity. So then order of X is defined to be minimum of all such R. So minimum of R in R n such that X power R is identity. Okay. If such no R exists, okay, so this is the definition of order. So what is a, I will make a remark. So you will define the order to be infinity, the order of X to be infinity or plus infinity if there exists no such R in N such that X power R is identity. Okay. So order of X is in particularly finite if there exists R such that X power R is identity. So if there is no such R such that X power R is identity, then you define it to be infinite. Okay. So here is an important observation about the order. Okay, that actually comes from a division algorithm. Okay, suppose assume that X is in G such that order of X equal to some n which is finite. Okay. So in case if we have X power D equal to identity for some D, for some D in N. So this is some other D natural number such that X power D equal to identity. So then what one can prove? We can prove that this order of X, that is N, must divide this D. Okay. So this is, you can call it a lemma. So how one proves this? So here is the proof. So we just use division algorithm. Whenever you see a statement that says one number is dividing another number, then you simply use division algorithm to prove that. Okay. So first of all, from division algorithm, this order of X dividing D is equivalent to proving the remainder to be 0 when you divide D by order of X. So let us use division algorithm. So using division algorithm, we know that there exists unique Q and R in EZ such that this D equal to Q times order of X plus r, where r satisfies r greater than or equal to 0 less than this order of x. Okay. So, now what we can do, we can just simply compute the power of x, okay, using this equation. So, if you compute the power, you can see that x power d is same as x power order of x times q times x power d. Note that x power d is identity, that is what given. So, x power d is identity. By the definition of order of x, we know that x power order of x is identity. So, x power d identity and x power order of x identity. So, this gives us identity equal to x power identity power q times x power d. So, this you get from this equation. So, you take one, substitute 2 in 1. So, then that implies identity equal to x power d. So, that implies x power r. So, I call this remainder to be r. So, that implies x power r is identity. So, now note that what is the property of r? So, r is some non-negative numbers less than order of x, but by definition of order of x, it is the minimum positive natural number such that x power r is identity. So, that means this r has to be 0. Okay. So, that proves that this order of x must divide d. So, now using this lemma, you can actually immediately write down this corollary. So, this actually gives another definition of order. So, you fix x in G such that order of x is finite. So, then what one can prove, order of x is nothing but minimum of those d dash inside n such that x power d dash is identity and d dash is dividing d. Okay. So, you also assume that x power d is identity for some d in n. Okay. So, basically what we are trying to say, so since you know that x is having a finite order, so there exists some natural number such that x power d is identity. So, if you are able to find one such natural number, then to actually find out order of x, so all you need to do is take all possible divisors of that d and then such that x power d dash becomes identity. Okay. So, basically to look for this order of x, you can only look at only the finitely many divisors of d such that x power d dash is identity. Then if you pick smallest among them, then that will be the order. Okay. So, this is immediate from the definition. So, why? Because, so from the lemma we can easily see that if you call this minimum to be, let us say, k, so then x power k being identity will imply that order of x is less than or equal to k, because order of x is the smallest number such that x power order of x is identity. So, now since x power k is actually x power order of x is identity. So, and that would imply that x power d is identity, x power d is identity, and that would imply that order of x divides d. So, that means this k has to be less than or equal to order of x, because k is the smallest divisor such that x power k is identity and k divides d. So, then if you put them together, you can see that order of x must be equal to k. So, basically this corollary tells you that once you know for some power x power d is identity, then to find out order of x, you can only look at the divisors of the d and then such that x power d dash is identity, take the smallest among them. Okay. So, now let us see some more properties of this order. Okay. So, now again let us start with some x in G such that order of x is finite. Okay. So, now we can actually take all other powers of x and then see what happens to them. Okay. So, since x power r is identity for some r because r of x is finite. So, that would immediately implies that if you take any other power of x, that also will be having finite order. Okay, that is immediate. So, in particularly what will be the order of some power of x. So, if I take some x power d and then the order of x power d will be exactly equal to order of x divided by the GCD between order of x comma d. Okay. So, let us prove this. So, let us start with the right hand side and then we will increase the power of x power d by that and then see what happens. So, you take x power d and then increase by r of x divided by GCD of r of x comma d. So, then this can be rewritten as x power d divided by GCD of r of x comma d times r of x. Since GCD of r of x comma d also divides d, so this will be some natural number. So, if you replace this order of x power d divided by GCD of order of x comma d, then you get this is exactly. So, this becomes identity. So, identity power something. So, this is identity. Okay. So, here I am using this fact that x power m power m dash is same as x power m dash power m. So, this is something we seen about exponential notation. Okay. So, there is no problem with this. So, now you can see that order of x power d definitely should divide. So, order of x power d definitely should divide this order of x divided by GCD of order of x comma d. In particularly it is smaller than the right hand side number. So, now what happens? So, we want to prove that. So, this is the exactly the order. Okay. So, there is nothing else actually smaller than this divides. So, let us call this order of x power d to be k, okay, and then see what happens. So, now if you call that k, then x power d power k becomes identity. So, now you can see that x power dk is identity. So, now this implies that order of x must divide dk. So, now from this it is easy to see from elementary number theory, this is something I already proved. So, order of x divided by GCD of order of x comma d should divide dk divided by order of GCD of order of x comma d. Okay. So, because this implies this order of x divides dk will imply dk equal to r times order of x. So, now you can divide this GCD of order of x comma d by both sides. So, then you get d divided by GCD of order of x comma d k equal to r into order of x divided by GCD of order of x comma d. Since this is an integer, this is an integer. So, that tells you that order of x divided by GCD of r of x comma d divides dk divided by GCD of r of x comma d. So, now note that this GCD of this r of x divided by GCD of r of x comma d divided by GCD of r of x comma d. So, this is relatively prime. So, now using this Euclid's lemma, you can see that this number must divide k. Okay. So, that means, so this implies order of x divided by GCD of order of x comma k order of x comma d must divide k. But already we got that k is actually k divides R of x divided by GCD of R of x comma D. So, that means k is smaller than this. So, now we have proved the other way, R of x divided by GCD of R of x comma D divides k, both are non-negative integers. So, that forces that k must be equal to, so which is nothing but R of x D, R of x divided by GCD of R of x comma D. Okay. So, this is just again uses the facts that we proved in elementary number theory. Okay. So, here is an immediate corollary. So, in case D divides n, okay, if D divides n where n is order of x, so then it is immediate that order of x power D must be equal to n divided by D. So, why? Because the GCD of n comma D will become D. Okay. So, it is immediate. So, now let us look at what happens if order of x is infinite. So, if order of x equal to infinity, so then it is not hard to see the order of x power D must be infinity for all D in n. Okay. So, why it is the case? Because if order of x power D is either it is finite or infinite. Okay. If it is finite, so then what will happen? Then there exists R such that x power D power R is identity, but that would imply that if x power D power R is identity, then that would imply that x power R D is identity. So, that would imply that R of x is also finite, okay, but that gives you contradiction. So, that proves that if R of x is infinity, then R of x power D must be infinity for all powers. Okay. So, now let us look at what happens if we take product of two elements. Okay. This is also very important important thing to understand. So, if I start with two elements, okay, let us assume G to be a group. Okay. So, you start with two elements A comma B and G. So, then is there anything that we can say about the product AB? The thing is we can't really say much about the order of AB in the general group G. Okay. So, I will state a theorem which I will not prove it now, maybe because it requires some sophisticated language, for example finite fields and this matrix groups over finite field and all. But I will tell you like what group is involved in the proof, but it is again like it is not too deep proof or anything, but the fact is actually very important fact. So, what this theorem says, okay, if you start with any integers, so what we are interested in understanding, okay, let us say you have two elements A B inside G such that order of A is m and order of B is n. Okay. So, now the question is what can you say about order of AB? Can we say anything? Okay. For example, definitely order of AB can go down very much. For example, if A is B is just A inverse and m equal to n. Okay. So, then the product AB will become identity. So, then order of AB will becomes 1. So, it can go very much down. But the thing is can it be very arbitrary? So, that is the question that we are asking. Under some circumstances it can't be arbitrary. Okay. For example, one such case is if order of if A and B commutes, then at least we can say that order of AB must divide the LCM of order of A order of B. Okay. That is something we can conclude if AB commutes. But if AB does not commute, then we do not have any handling. Okay. That is what this theorem says. So, for any integers m, n, r which are greater than or equal to 1, so there exists a finite group G with elements A comma B in G such that order of A can be m, order of b can be n, and order of AB can be just R. So, there are no relations between the order of A, order of B and order of AB. So, that is what this theorem says. So, basically the group will be something like SL2FQ modulo plus or minus identity. This modulo plus or minus identity is not that important, but anyway. So, this finite field FQ is what important. So, you have to choose a Q very cleverly such a way that you set up this group SL2FQ modulo plus or minus 5, and you can construct some matrices 2 by 2 matrices A and B satisfying these properties that we have told. Okay. So, this is actually known result in the literature. So, this maybe I give this proof of this later. Okay. So, I will outline little bit about finite field and then we will come to this later. But now what I want to do, I want to say what we can say under some circumstances about order of AB. So, one thing that we can say, if AB equal to BA, so then order of AB must divide LCM of order of A and order of B. Okay. And that is easy, you call this LCM L, then if you raise AB power L, if you show that AB power L is identity, then you are done. But since A and B commutes, then AB power L is same as A power L, B power L. Since L is multiple of A as well as multiple of B, you can see that A power L must be identity as well as B power L is identity. So, L is some k times order of A. So, it is some k times order of A. Similarly, L is some k dash times order of B. Okay. So, that tells you that both the powers are identity. So, that means AB power L is identity. So, order of AB must divide the LCM. So, now further if you assume this order of A, order of B both are relatively prime, then you can definitely say what will be the order of AB. Okay. So, let us look at that. So, you assume again AB is BA and GCD of order of A, order of B you assume to be 1. Then what we can say, so then we can prove that order of AB is exactly equal to order of A times order of B. So, as before we call this order of A M and then order of A N. So, then order of AB we want to show it is Mn. So, we already shown that so order of A times order of B is nothing but LCM of order of A, order of B, because GCD is 1. So, that means AB power this order of A times order of B is identity. Okay. That means order of AB divides this. So, no issue. So, now we want to show that if you call this is D, okay, then this D must be more than this order of A, order of B. So, let us see how to prove. So, we know that AB power D is identity because AB order of AB is D. So, now this implies A power D, B power D is identity because AB commutes. Okay. So, this can be again rewritten A power D equal to B power minus D. Okay. Now, if you take order of A on both sides, then A power D times order of A is equal to B time minus D times order of B. Now, you can see that A power order of A is identity. So, the left hand side becomes identity. So, that means B power D order of B order of A is identity. So, that would immediately imply order of B divides D times order of A. But note that the GCD between order of A, order of B, it is 1. So, they do not have any common factors. So, that means order of B must divide D, okay, from this. So, now similar argument again will show because A power D is equal to B power minus D. Now, you raise it power order of b. So, then what happens? So, a power d order of b will become identity. So, that will show that order of a divides d times order of b, because order of a, order of b both are relatively prime, that will imply that order of a divides d. So, now what we proved? We proved order of a divides d, order of b divides d. Now, since order of a, order of b both are relatively primes, so that means the product also should divide. So, this is again we proved using Clewit's lemma. So, that means d must be greater than or equal to r of a, r of b. So, but already we proved that d must be at least r of a, r of b. So, that will imply that d equal to r of a, r of b. Okay. So, this indeed says what happens under some particular circumstances, what happens to the order of a b. So, when order of a and b commutes and the order of a, order of b they are relatively prime, then you can guarantee that order of a b equal to order of a times order of b. So, like I said, if you take a equal to b, b equal to a inverse, then a b will become identity. Okay, the order can drop down very much. So, you have to be very careful. So, now let us see how many elements you will have inside, okay, given a group. So, let us start with some element, okay, let us say g, and then there is this x such that order of x is finite. So, then we can look at this subgroup generated by x. Okay. So, this let us call this R of x is n. So, then you know that the number of elements in this subgroup generated by x, that must be exactly n. Okay. This must be identity x, x square, etc., x power n minus 1. So, why? Because if there is some power x power I equal to x power j with I less than j, and then like between 0 and n minus 1, then what will happen? Then x power j minus I will become identity, but j minus I both are smaller than n. So, that will force that this is greater than or equal to 1 and then less than n, which is a contradiction, because n is the smallest number such that x power order of x is identity. So, we can't get any smaller power of x such that x power that is identity. Okay. So, that indeed says the elements identity x, x square and so on x power n minus 1, they are all distinct inside G. So, that proves that the cardinality of the subgroup generated by x is exactly the order of x, which is n. Okay. So, now what happens if you take order of x is infinity? If you take order of x equal to infinity, then you can see that the subgroup generated by x, so this must be having all these elements identity x plus or minus 1, x plus or minus 2 and so on. So, you have the positive exponential x, x square and so on. Similarly, their inverses x inverse, x power minus 2 and so on. So, this must be there inside this subgroup. So, now our claim that all these elements are distinct. Okay. So, that means there is a one-to-one correspondence between z and this. Okay. So, this is inside G. So, the cardinality of this is also infinite, that is what I want to say. So, why that is true? Suppose let us say you have x power I equal to x power j. Again, now I j can be integers. Okay. So, without loss of generality, you can assume that I less than or equal to j. If I equal to j, then there is nothing to say. So, for some distinct I j, let us say x power I equal to x power j. So, then what happens? Similarly, as before, x power j minus I becomes identity. Okay. But j minus I is non-zero, because we assume to be j is greater than I. So, it is non-zero. So, that means there exist. So, this also becomes actually positive. Okay, j minus I becomes positive. So, there exist some natural number such that x power j minus I equal to identity. So, that forces that order of x is finite, but you have started with order of x infinite, which is a contradiction. So, that tells you that these elements identity x plus or minus 1, x plus or minus 2 and so on, they are all distinct. Okay, this is, you can rewrite as x power j dash j dash in integers. Okay. So, that means this group generated by x that has infinitely many elements. Okay. So, basically we will define a group is cyclic if it is generated by one element like this. Okay. So, in the next class I will use all these properties that I proved and then understand what are all the cyclic groups and then more about cyclic groups. I will stop here, we are running out of time. I will continue in the next class. Thank you.